Okay, so dear colleagues, it's now time to start our evening, or for some people afternoons, maybe for some people morning session, I don't know, evening in Asia anyway. Dehn, so our next speaker is Professor Mahender Singh from Mohali, and he will tell us about Dehn quandles of groups and surfaces. So let's welcome.
Thank you, Professor Mantro, for kind introduction. Let me take the opportunity to thank the organizers for this kind invitation and organizing this wonderful conference. So I'm going to talk about Dehn quandles of groups and surfaces. So this is going to be a rather elementary talk, and I hope I'm going to produce something. So this is based on some joint observations that we made with two young postdocs at Mohali, Hitesh Raundal and Neeraj Dhanwani. So I will start with something very basic. So experts may please excuse me. Okay. So it's a knot theory conference. Everybody know what knots and links are. So let me complete the formality by giving definition. So a knot is an embedding of a circle in R3. Okay. And we say two knots are equivalent if they are ambient isotopic. So ambient isotopic is simply a continuous map from R3 cross 01 to R3, okay, such that at each, you can consider it as a time parameter. At each time, it's a homeomorphism, starting with identity and mapping first knot to the second. Okay. One can imitate the same definition and write it down for links. I will not write it down. And showing that whether two knots are equivalent, two knots or links are equivalent is in general difficult. So fortunately, there is a relatively easier way to study knots via planar four-valent graphs with knot diagrams. So a knot K in R3, take a knot K in R3, and and we project it on the plane. We call a regular projection. If pre-image of each point is either 1 or 2 points, you just avoid the vertices. Okay, and these projection with over and under information is called a knot diagram. Okay, so Kurt Reidemeister proposed the following moves on diagrams of knots. They are called the Reidemeister moves. So the first move is here, straightening the arc. Second move is just sliding one over the other, and here is the third one. So I'm writing these trivialities for a purpose because my talk is all around quandles, and quandles are just algebraic formulations of these very natural moves on planar diagrams of knots and links. Okay. So thanks to this theorem of Reidemeister and Alexander Briggs proved more or less at the same time that two knots or links are equivalent if and only if. So throughout my talk, I will be writing knots, but most often it will mean knots and links both. So please excuse me for that. So two knots and links are equivalent if and only if knot diagrams can be transformed from one knot diagram of one can be transformed into knot diagram of the other by a finite sequence of Reidemeister moves. Okay. So here is an example. So here on the right is a familiar picture of the trefoil. On the left is not so familiar, but as you can see, one can transform one into the other by a finite sequence of Reidemeister moves. So here comes quandles. So I mentioned about the three Reidemeister moves. So we'll see that those moves can be formulated algebraically as follows. So what is a quandle? A quandle is a non-empty set with a binary operation, okay, which we denote by star. We satisfy three axioms. The first is the idempotency, and the second one is the bijectivity of the right multiplication. So existence shows subjectivity and uniqueness shows injectivity. And the third is right distributivity. So Z acting on star of two element is star of Z acting on the individual ones. So although these objects had been studied in the past under different names, in the Japanese school at least they were called keys in the work of Takasaki on finite geometry. But I think the true momentum really came after fundamental works of Matveev and Joyce, where they related them to knots. okay, found not invariants. And since then it has been a very popular topic. So so this exam, as I said, equivalently you can define it in the form that for each element of this set with this binary operation, the map Sx, which is right multiplication by x, is an automorphism of x. It's a morphism of this set with the given binary operation. Okay, and these are called the basic inner automorphisms. All right. They generate a nice subgroup of the full group of automorphisms called the inner automorphism group. And bijectivity of each Sx is actually equivalent to existence of a dual operation, which you can call star inverse. So you just write x star y equal to z if and only if x is z star inverse y. Okay, these are fairly easy observations. And these exams are just reformulation of the three right-dimensional moves. So take a knot diagram, so you can orient it if you like, and you set the rule that the over arc y act on the incoming arc x, and the output is that action x star y. And if the orientation, if the crossing is negative, then you just set it as x star inverse y. And if you follow this rule, it is not difficult to check that the first right-dimensional axiom R1 is equivalent to idempotency. The second is equivalent to this equation that x star y star inverse y is y. So I should have labeled this on the left as well. But that is equivalent to right multiplication by y being bijective, okay, being invertible. And if you do the diagram chase for the third right-dimensional move, you see that the leftmost tip here should be the same as the right one. So you get this side equality. X star y star z is x star z star y star z. Okay. So the axioms are just tailor-made for the three right-dimensional moves. So as one can guess, so knots and links should give rise to quandles. So loosely what you can do, you take an oriented knot or a link and take this abstract quandle. So the category of quandles is very nice. You have free objects, so you can talk about presentations and you can develop all that algebra. So you can associate a quandle to a knot or a link by just taking the generators as arcs in a diagram, and the relations at that each crossing, the over arc act on the incoming arc, and the output is labeled as that action x star y. Okay, so if y is the over arc separating this arc x and z, then z is x star y. Okay, and it requires some effort to check that it's invariant under, it's independent of the diagram we choose and all that, but it can be done. So all this is attributed to Joyce and Murphy. For example, if you take this simple link, the trivial link, okay, so there are no crossings, so no relations. So this is simply the free quandle on n generators, where n is the number of components in this trivial link. Okay, and Joyce and Murphy proved that if k prime and k are two oriented knots, then k prime is equivalent to either k or the negative or the mirror image if and only if the knot quandles are isomorphic. So it's a very strong invariant. In fact, many well-known knot invariants can be recovered using the knot quandle. For example, as we will see the knot group K, the link group, because it will be relevant to my discussion. But in fact, many other invariants, in fact, the hyperbolic volume also you can recover using a closed cycle. There is some work of, I can't remember the name, but from somebody from Japan. All right, so let us see some examples. So we already see that quandles come from knots, but a lot of algebraic structures, as we already saw in a couple of lectures, a lot of other algebraic structures also gives rise to quandle structures. Okay, so the simplest being from the groups. So if G is a group and you fix an integer, then you can equip this set G with this new binary operation, A star B is B inverse A B to the power minus n. And it's a fairly easy check to see that this is a quandle. Okay, you denote by this. And the case n equal to 1 is of particular interest. That's called the conjugation quandle. Okay. Another way is that you take a group and fix an automorphism. And you define this operation A star B as phi of A B inverse times B. One can check it's you can think of it as a non-abelian version of what are called Alexander quandles, like defined over the ring of Laurent polynomials and so on. So you can talk about this for any group. It's called the generalized Alexander quandle. And when the group is cyclic group of order n, typically written additively in this in knot theory, then this gives rise to what is called the dihedral quandle. Okay. And one more structure which will come up later in this talk is this operation. So you take a group and define A star B to be B A inverse B. Again, this is a quandle that's called the core quandle of the group G. Okay. And a special case of this, when G is an abelian group, they appeared in the work of Takasaki in finite geometry, and that's hence the name. They are also called Takasaki quandles. One interesting example from a little distant topic is Riemannian symmetric spaces. If you take a Riemannian symmetric space, which is just a Riemannian manifold with the property that at each point you have a globally defined symmetry which fixes the point x, then you can turn this manifold into a quandle by defining y star x to be action of the symmetry on y. Very natural definition. Here's an illustrative example. You take the sphere and fix an angle between 0 and 2 pi and define x star y to be the theta rotation of x with the center at y. And one can see that it gives you a quandle structure on the sphere. You can have plenty of more topological, smooth quandle structure. I'm sure they are of independent interest. The quandle of interest to this talk will be Dehn quandle. So let me define it very quickly here. I will come to this later on in detail. So if you take a surface sigma G and take dg to be the set of all isotropic classes of oriented simple closed curves, you can define a binary operation on this set. Take a simple closed curve alpha, take the another one, and you define the action of beta on alpha to be simply the image of alpha under the Dehn twist along beta. Okay. So for example, if beta is this curve labeled red and alpha is another curve, then you just rotate this alpha along beta when you near approach it. So my Dehn twist here is the right side, right Dehn twist. So I turn alpha, if I move from left, I turn toward the left. Okay, I turn toward the right, move it along this red curve, and then move along the remaining path trajectory of alpha. Okay, you can see that you don't really need an orientation here. If you would have moved from the right side to left side, you would have got the same answer. So we will revert back to this example later on. So there is a way to go from quandles to groups. Okay. In fact, this conjugation quandle given a group G and its conjugation quandle, all these constructions that I mentioned in the first slide, in the example slide, they all are functorial constructions. Okay. So, and if X is a quandle, then you can associate a group to that called the enveloping group of X. In the more general framework of solution of Yang-Baxter equations, this is nothing but what they call the structure group. So how do we define this group? This group is simply generated by elements of the quandle, which just for clarity, we denote by just different notation EX. And the relations are simple that each star you replace by conjugation. So the generator corresponding to X star Y, okay, you equate it to conjugation of X by Y. Okay, so you just replace conjugation by the star by conjugation. Okay, and that is what the enveloping group is. For example, if X is a trivial quandle with say n elements, then a trivial quandle, by the way, is just X star Y is X. Okay, every element of the quandle act as identity on every other element. So then the enveloping group is simply this group generated by E1 to En, and this relations E of X star Y simply becomes Ex. So it's just a commuting relation. So this group is just free abelian group of rank n. Okay. One can in fact recover the link group from the quandle. So in fact, if L is a link, then the enveloping group of the link is just isomorphic to the link group. Okay, so let us come to the topic. So this is rather a very elementary observation. So what we saw is that there are a lot of work on different kind of quandles that various authors have done, and it turns out that many of them actually can be just seen as a special in one family, in one general framework. So this is what we try to frame, although it is very simple-minded. But we'll see where we go later on. So there are many constructions of quandles, including conjugation quandle, as I mentioned, the free quandle on a set, Coxeter quandles. These quandles appear in the work of Akita. Dehn quandles of orientable surfaces. So these, as I mentioned briefly earlier, they appeared in the work of Zablo, I think his PhD thesis, and also studied later on by many other authors. Quandle of chords of orientable surfaces. I think it's in the work of Saichi Kamada, one of the works of Saichi Kamada, and knot quandles of prime knots, of course, we know, and core quandles of groups, generalized Alexander quandles of groups, all these examples that I mentioned. So what is the situation in all these quandles is that they are just sitting inside conjugation quandle of some group. That is what the observation is basically. So one can take an abstract group G and a normative set and take AG to be the set of all conjugates of elements of A in G. Okay. Then we call this set to be the Dehn quandle when we just consider the operation to be conjugation. Obviously, it's a quandle, okay, with respect to conjugation. In fact, it's a subquandle of the conjugation quandle. And this name we are just borrowing from the work of Zablo. That was our original motivation to study Dehn quandles of surfaces. And also these, because these quandles are just union of conjugacy classes whose study dates back to Dehn, so as a name. But we will see that these are already, I mean, in the literature, these we'll see that these quandles are simply those which embed into their enveloping group. So let me remark here a similar construction of Valery Bardakov and Timur Nisibilo in 2020. So motivated by the construction of free quandles of groups, they gave a little general construction. So let us see that. So take a group G and a subset of the group. And on this Cartesian product A cross G, we define this binary operation. So AU star BV is A, and you conjugate V by U and multiply by V. Okay, so U V inverse B, conjugate B by V and then the right multiplication by U. Okay, let us denote this. So one can check it's a quandle. And in case your group G is a free group and S is a free generating set, this gives you what is called a free rack. Okay, this is a rack. So for quandle, you need to go to modulo some relation. So the relation is that you equate A VU to be AU whenever this V is in the centralizer of A in G. All right. And let us denote by the square bracket to be the equivalence class of the element AU. And one can check that there is a well-defined binary operation on this quotient set. And in fact, that's a quandle. So in the special situation, this gives you the free quandle, but this is quite a general class of quandles. And if you recall the definition of what is what we call Dehn quandle, it is just union of just the set of conjugates of A in G. So what Bardakov and Nessie below proved that the G, they actually refer these as GA quandles. So the quandle QGA is isomorphic to the Dehn quandle, if and only if elements of A are pairwise non-conjugate in G. So therefore, this actually excludes a lot of lots of other quandles which are actually sitting inside the conjugation quandle. Okay, so that was our take, that maybe if you consider just conjugates of arbitrary sets, we get a little different family. And in fact, that is the case. For example, a lot of Artin groups, Coxeter groups will lie in, braid groups will lie in that family. So Dehn quandles of groups so of course it depends on the group, it depends on the subset that I choose. So when the subset is a generating set, this is of particular interest. So the following observation is very basic, but quite useful, as we will see later on. So if G is a group generated by the set S, then the Dehn quandle is as a quandle is generated by the same set S. Okay, this is extremely elementary, but let me give you the proof. So if you take an element, so it's you write it, it's a conjugate of the generator, and then that generator you write in word and just rewrite this expression in terms of the star operation, because you know the conjugation is the star operation is conjugation. So just rewrite it. Okay, that's it. But the difficulty is finding the relations, how to translate all the relations in your group into quandle relations. If I give you a Dehn quandle, how to write the precise presentation of that? So that is what we will achieve toward the end. Also, there is a nice relation of the enveloping group in this case with the underlying group. So suppose you S is a generating set for your group, then there is this map from the enveloping group of your Dehn quandle to the group G. What does it do? It just map EX to X. Okay, and because it's generated by G is also generated by S. Okay, so we just need to check to satisfy the relation or not, but they do satisfy this relation because it's tailor-made for that, and therefore you have a surjection of the enveloping group of the Dehn quandle onto your group. And in fact, it turns out that it's a central extension of groups. So this, when the group under consideration is a Coxeter group, this was considered by Akita in a fairly recent work. And further, if the abilinization has torsion, then we know that this extension does not split. Because it's a central extension, if it splits, it's simply a direct product. And if the abilinization has torsion, you arrive at a contradiction, because abilinization of the enveloping group will not have torsion. The second statement is rather trivial, but and also showing that it's a central extension, one just have to use the definition actually. Okay, and in fact, the map turns out to be injective in some cases, and the cases are as follows. If you take a group with a presentation such that the relations are only of the conjugation type. Okay, that means if SNT are two generators, the only relations are that WS, W inverse is T for some element W in G. Then, in fact, the enveloping group is precisely the group G. For example, so if you take an Artin group, so let me recall it briefly. So these are, let us take finitely generated here. So finitely many generators, and the only relations are this words SI, SJ written in this iterative form. SI, SJ, MIJ simply means SI, SJ, SI, SJ, so on. The total length of the word being MIJ is equal to SJ, SI to the power underscore MIJ. Okay, and since these groups satisfy the relations, so for if you consider Dehn quandles of Artin groups with Artin generating sets, the enveloping groups are just the group themselves. Okay, just obvious consequence of this simple observation. And as I remarked earlier, so these quandles are simply the ones which embed inside this. So how to see that? It comes directly from the universal property, okay, of this map. So take a quandle Q and let ENVQ be the enveloping group of the quandle. We know there is a natural map which sends the quandle element X to EX, okay. And in fact, if you view enveloping group as a conjugation quandle, one can check it's a morphism of quandles. You can see it as inside map from Q to conj of enveloping group of Q. And given a quandle homomorphism F from the quandle Q into conjugation of any group, there is a unique group homomorphism, let us call it F hat, from enveloping group of Q into G, okay, such that this holds, such that the diagram, natural diagram commute, okay. So eta followed by F hat is F. So this immediately lead to this following characterization, excuse me, that a quandle embeds inside the conjugation quandle of a group, let us say H, is equivalent to the statement that the natural map from Q to enveloping group is injective. And that is equivalent to that Q is actually the Dehn quandle of some group where S is a generating set for this. These are extremely simple implications, just basically consequences of this universal property. So in the literature, quandles for which this map is injected, they are also called faithful quandles. So Dehn quandles are just faithful quandles. And it's a recent work of Bergman, where he proved that core quandles are in fact quandles of this type. So for each core quandle, you can find a group such that the core embeds inside the, is isomorphic to the Dehn quandle of some group. Okay, so it embeds inside conj of H for some group H. In fact, if you take a fixed point free automorphism of a group, then one can show that the generalized Alexander quandle is also a Dehn quandle. Okay, basically in that case, this map is faithful. So core quandles, Dehn quandles, core quandles, conjugation, and generalized Alexander quandles are quandles of this type. So let me now focus to the Dehn quandles of surfaces, which we will see they are nothing but Dehn quandles of the mapping class groups. And then we will try to say something about the presentations. Okay, so let SGP be an orientable surface of genus G with P punctures. So I have written punctures here, but we will view them as mark points, not really the point, the points being removed. So there are various conventions in this subject, so we have stuck to this. The mapping class group MGP of SGP is then defined as the set of isotopic classes of orientation preserving self homeomorphisms, which permute the set P of punctures. This is a very well studied group. A simple closed curve in SGP in the surface G with P mark points is an embedding of a circle into the interior of the surface. Okay, so I don't want my curve to really go through these mark points. We say that such a curve is essential if it is not homotopic to a point or is also not homotopic to the mark points. A simple closed arc is an embedding of the unit interval into the surface, okay, such that the pullback is just 0, 1. So endpoints of these are just those mark points. Endpoints of this image of the interval are just the set of mark points. And we say such an arc is essential if the endpoints, the values at the endpoints are different. So we will be dealing with essential simple closed curves. So in the later slides, by abuse of notation, so I will use the same notation for the isotopic class as well as the curve or the arc representing it. Okay, so given a simple closed curve alpha and a simple closed arc B on the surface SGP,
it's 3 o'clock.
So we denote the right-hand Dehn twist along alpha by tau alpha, and the anti-clockwise half twist about the arc B by HB. Okay, so here is the Dehn twist of beta along alpha, which we denote by tau alpha beta, and here is the half twist. So just focus on the vertical red one, and I'm taking half twist along this arc, joining these two dots. Okay, and that is what exactly this is, the S-shaped arc, HBA. So these the half twist and Dehn twists are of fundamental importance because they are the generators for the mapping class groups. So let DGP denote the set of orientation isotopic classes of all simple closed and simple closed curves and simple closed arcs on the surface. And we say a simple closed curve alpha is non-separating if the closure of the complement of the curve on the surface is connected. Okay, and of course separating otherwise, and separating and non-separating simple closed arcs can be defined analogously. And let DGPNS be the subset consisting of isotopic classes of all non-separating simple closed curves and simple closed arcs. Okay. So this is a subset of DGP. So to each isotopic class Y belonging to DGP of a simple closed curve, we can associate one can define the Dehn twist Ty to be one can define Ty to be the isotopic class of the right-hand Dehn twist. So I'm just again abusing the notation, using the same notation for the Dehn twist as well as its isotopic class. Similarly, one can do for the simple closed arcs, denote the half twist by the same notation. And then one sees that you have a map from this set DGP to MGP. Okay, under this convention, which simply maps X to tau X if X is the isotopic class of a simple closed curve, and HX if X is the isotopic class of a simple closed arc. So the set of all Dehn twists along non-separating simple closed curves form a single conjugacy class. This is a well-known fact. In fact, one can check that if phi is a homeomorphism and alpha is a simple closed curves, then the Dehn twist along phi image of alpha is simply the conjugation of Dehn twist along alpha by the homeomorphism phi. Okay, so, and if S is a generating set for the mapping class group consisting of Dehn twist and about simple closed curves and half twists about closed arcs, so one can always take this set to be finite. Okay, it's well known in this subject. One can choose, for example, Humphreys generators, which we will show in coming slides. And therefore, as I said, DGP is just the set of conjugates of these generators in the mapping class group. Okay. And so this S superscript MGP has a quandle structure, the natural conjugation. Okay, therefore this DGP has a quandle structure, and it's called the Dehn quandle of this. So, and this is precisely the quandle structure, just you can define by action of the Dehn twist. So to be explicit, the quandle operation in DGP one can define like this: X star Y is tau Y of X if Y is the isotopic class of a simple closed curve, and HY of X if Y is the isotopic class of a simple closed arc. This I had mentioned briefly in the one of my first slides. And in fact, the map tau that I defined in the preceding slide is an embedding of quandles. That's very obvious because a simple closed curve mapped to the corresponding Dehn twist and a simple closed arc being mapped to the corresponding half twist. Okay, these are faithful maps. And that shows that it's an embedding of quandles. So tau of X star Y is basically just tau X star tau Y. So a bit of history on on Dehn quandles of surfaces. So Dehn quandles of surfaces without punctures appeared in the work of Zoe Zablo in his thesis, and then Kamada and Matsumoto also, and yet in 2000 and 2003 respectively, they considered quandle structures on the set of isotopic classes of simple closed arcs. Okay. what they referred as quandle of chords. So we have tried to consider the general situation, but the arguments are basically similar. And in general, the quandle of chords is a subquandle of DGP, just from the very construction. And in the case of a disk with n+1 punctures, this quandle can be identified with the Dehn quandle of the braid group. Okay, because we are just considering the chords. And soon after, there was a very amusing result of Niebrzydowski and Przytycki, which was our motivation for really looking at Dehn quandles. What they showed is that the knot quandle of the trefoil is isomorphic to the Dehn quandle of the torus. So, of course, this is looking at this result, is natural to see what really happens. Is there any deeper connection between knot quandles and Dehn quandles of surfaces? And it turned out not to be the case. So this was further explored by Zoe Zablo later on, where he showed that in fact this is really a isolated case in really an isolated case. So in fact I could have written here. So in fact what he showed is that if you look at the family of torus knots of the form T to P, where P is not divisible by 3, then then knot quandles of such torus knots do not have any non-trivial homomorphisms into Dehn quandles of surfaces. Okay. So they are really, this is really an isolated case. So therefore we were wondering what can we really say about morphisms from from knot quandles of other families into Dehn quandles of surfaces, but it seems it's a difficult problem because we don't really know presentations of Dehn quandles, and we'll say something about that in a few minutes. And from the very construction, it follows that one can say about automorphisms of Dehn quandles. So if you have a group and X a subquandle of its conjugation quandle such that the subquandle as a set actually generates the group, then it's very easy to show that the inner automorphism group of this quandle is simply the central quotient, which of course is isomorphic to the inner automorphism group of the conjugation quandle, which is a rather trivial fact. But this isomorphism can be deduced from an observation by Takefumi, which is which take motivation from the construction of augmented quandles. So I will not get into that, but using these observations, it's fairly easy to deduce that the inner automorphism of DGP non-separating is just the central quotient of the mapping class group. Inner automorphism of DGP, including all kind of curves and arcs, is also the same. And in fact, the automorphism groups are also the same. Okay. So the case when you don't have punctures was already considered by Nosaka in his earlier work. So what we do is that we include punctures, and the arguments are a little similar. But basically, all this follows from this simple observation. And in fact, from one of the first propositions that I mentioned, that if you have a Dehn quandle of a surface with respect to a generating set, then the same set generates the Dehn quandle as a quandle. So therefore, Dehn quandle DGP NS is generated by isotopic classes of these curves, and DG NS is generated by isotopic class of these curves. These curves you can see in the figure as follows. So A1, A2 are these as here, the meridians, and B1 to BG are around each genus, C1 to C are these curves, and A1 to A23, these are the curves which are transfers to the segments. Okay. And similarly, I mean, if you don't have puncture, then the picture is even simpler. Okay. What about now the question is, what about the relations for Dehn quandles of surfaces? So here is what we are able to show, which is not difficult, but in some cases it do give us some nice presentations. So let us take a group G with a presentation SR, not necessarily finitely presented. So for each generator S, let AS be the generating set for the centralizer. And let T be the set of all pairs of generators which are conjugate, and T be a choice function from this set T to G, which basically just chooses the conjugating element in a way that we satisfy these nice properties, which one can do, okay, in almost each case. Then the Dehn quandle has a presentation with generating set S and defining relations as follows. So though they look complicated, they are very natural. The first two relations are direct consequences of the presentation of R actually, and the fact that AS is a generating set for the centralizer. So you choose a generator S of the group and a relation R, but then the relation as a word is trivial, so we just conjugation by that is just the element. So you just write in the quandle form. Okay. Similarly, you choose a generator and a word in the generating set of the centralizer, which I rewrite in the generating set of my original group. Okay. Now, because it's a centralizer, again, it conjugates, fixes the element. So which in quandle form is just this relation. And the third one is that given a pair ST in T of conjugating generators, conjugate generators, okay, and let FTS be the word, the group element which conjugates. So I write it in this form, okay, where FITS is element of my generating set. Then we have this relation, which is just conjugation I have rewritten, okay. I have just rewritten in the quandle form. But in fact, one can shorten some of these, one can reduce the number of relations in the following, by the following procedure. So relations of type 2 need to be checked only for those generators that represent distinct conjugacy classes. And if two or more generators represent different conjugacy classes, then you just partition your set of generators and equip each xi with a partial order, okay, such that the corresponding poset graph is a tree. Then each relation of type 3 need to be checked only for those which are adjacent in this poset one. So that reduces the number of relations drastically. And obviously, the way we have given this presentation, it follows that if the group is finitely presented and centralizer of each generator from the generating set is also finitely generated, then the Dehn quandle is finitely presented. All right, so I have a few more minutes. So in the last few slides, let me illustrate two examples. So look at the Genus2 oriented surface, which is the torus. Then we know that the mapping class group of this has this presentation. It's well known. For example, one can see Farb and Margaret's book. So it's generated by Dehn twists along the longitude and the meridian, TA and TB, as you can see in the figure. And there are two relations. One is a braid relation. TA, TB, TA is TB, TA, TB, and other is this relation that is TA, TB to the power 6 is just 1. Okay. So applying the theorem, let us set the set S to be TA, TB. Okay. Here we have only two, and we know that TA and TB are conjugate, so we don't really need to bother about the ordering of the generators. Okay. And we choose the conjugating element, the choice function to be TA, TB. Okay. Then we can easily, we know centralizer of the Dehn twist along A is generated by this. If we know it's fine, but we can actually get it directly. Here is a small illustration. You look at the symplectic representation of this mapping class group into SL2Z, okay, which is basically just the induced action of the mapping class group on the first integral homology of the surface. And in this case, it's an isomorphism, okay. And one can check that at matrix level is little easy to see that centralizer is here, is denoted by image of TA and minus identity. where minus identity is the third power of this product, psi TA times psi TP. And therefore, centralizer of TA is just this element. Therefore, applying the theorem, we will have that the Dehn quandle of the torus will be generated by the set S and these defining relations. This is given by theorem, but you can see that some of them are you can actually throw away, and some of them you can rewrite. And doing that dirty calculation, one can see that the Dehn quandle of the torus is just this quandle, which is generated by two elements, and these relations TA, TB, TA is TB, and the interchanging role of A and B, which are just braid relations written in this form. But one should note here that the braid group, we have only one relation. In the braid group B3, we have only one relation. But here, when you pass on to the quandle level, then you really need the other relation. You can't just, I mean, this quandle won't be generated, won't have only one relation. You need two, okay? But if you recall, if you try to write down presentation for the knot quandle of the torus, this is precisely the presentation of the knot quandle of the torus. Okay, so this is another proof of this amazing result of Niebrzydowski and Przytycki, which is rather short because they use different arguments. And similarly, one can write presentations of mapping class groups of higher genus, which will be a little messy in the sense that because you need to know the centralizers and which perhaps are known, but then you'll have a lot of relation, you need to do the reduction. But I think it is doable. So let me, in the last slide, show you the presentation of the Genus2 case. So here is the Genus2 surface. And what I have marked these two meridians, A1, A2, and this B1, C1, B2, or the isotopic classes of the Dehn twist along these curves, they generate the mapping class group. So just for ease of notation, I just relabel them as alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. And we know that the mapping class group has this presentation. This is well known. So let us see how what is the presentation of the Dehn quandle. So I order these generators in this form. And because they all are non-separating simple closed curve, they all are conjugate. So I just need to bother about only centralizer of only one generator by the remark that I made earlier. And we choose the choice functions for conjugating element to be like this. And it's a result of Putman. These are, it's in some lecture notes, perhaps it should be there in some works, that the centralizer of the curve alpha 1, okay, recall here, alpha 1 is the Dehn twist along A1, is the hyperelliptic involution. Okay. Is generated by this, these isotopic classes of Dehn twist along this curve, where I is the hyperelliptic involution. Okay, and this identity is easy to show in this case. Then using the theorem and doing a rewriting process, one can write down the presentation of the Dehn quandle of Genus2 surface, which is precisely in this form. Okay. So we believe that writing, if you can write down the presentation of the Dehn quandle of a Genus2 surface, and using that we of course get the presentation of the enveloping group of this quandle. And it is known that there is a work of Gervais which relate the enveloping group of the Dehn quandle with the universal central extension of the mapping class group for genus, of course, G bigger than or equal to 3, because you need it to be perfect. So it seems that presentation of Dehn quandle, we can get a finite presentation for the universal central extension of the mapping class group, which I'm not sure that is known. There is a paper of Gervais where he write a presentation, but it's infinitely present. It has infinite number of generators. And I think if we use the Dehn quandle approach, there is a possibility to write a finite presentation for the universal central extension of the mapping class group. And the last remark that I would like to make is using once we have presentations of this higher genus Dehn quandles, then maybe one can answer which knot quandles can be colored non-trivially by Dehn quandles of surfaces, other than torus knot quandles, which has already been considered by Zappo. So with this, I will stop here. Thank you for your attention.
Okay, Professor Singh, thank you very much for a very interesting talk. Dear colleagues, are there any questions or comments? Please unmute your microphones if you have comments, or write on the chat line. Everything will work. Well, as far as I remember, there was a nice work on quandles by Richard Rubinstein when he was dealing with symmetric spaces, so that we could get an invariant of knots valued in. So possibly you can get invariants of knots valued in some moduli spaces, or I don't know. So when you use your various quandles.
Yeah, thank you. Yeah, thank you. I have seen that paper. So he constructs this an invariant which is a topological space.
Yeah, it's impressive. Yeah,
it's quite interesting. Yeah.
Okay. Okay, dear colleagues, are there any further questions or comments, remarks, maybe?
Hello.
Yes, please.
Yeah, Manpreet, I can hear you.
Thank you. Thank you for this nice talk. So I have one question. Suppose we have two different presentations of a group, and then what can we say about the Dehn quandles of those two different presentations? Are they related in some sense?
No, actually, I don't think so. We didn't really think seriously, but they will be different actually. In fact, if you take the different set of, they will be different actually. They will be different, certainly. They will be different. But it would have been nice if there were, one could find some relations. It depends very much on the presentation.
Okay. Suppose if we keep the relations, but we change the, we add some further generators. In that case, any idea how they will relate? Means, do you think there will be some relations? But we are keeping the same relation, but we are just adding some redundant, you can say, generators.
Yeah, then you have to see that the extra generator that you are adding, which conjugacy class they lie. So if they fall in the same conjugacy class, you of course get the same quandle. But if they are in different conjugacy class, you get a different set and therefore a different quandle.
Okay, thank you.
Yeah, actually, unfortunately, different sets, different generating sets, somehow they are not related. Yeah, it depends on the set.
Okay. Any further questions or comments? Well, if it's not the case, so let's